So we continue on the theme of attosecond and femtosecond molecular dynamics with the next talk by Franck Lepine.
Okay, good morning, everyone. So I would like to thank the organizers for giving me this opportunity to present our work. And in the next 25 minutes, I would like to show you a kind of overview of what we have been doing recently on complex molecules using XUV IR schemes. And we are especially interested in dynamics that are induced by the short XUV pulse and that are probed by the infrared pulse. So there will be a first part about ultra-fast relaxation on femtosecond timescale in pH molecules. And I would like to show you how this is connected to very interesting questions, very fascinating questions in astrochemistry. And then I will be discussing work in progress about sub-femtosecond timescale dynamics in these molecules, including attosecond interferometry experiments in pH and attosecond charge dynamics induced by electron correlation. So what's new with short XUV pulses? Well, they combine two interesting things: high photon energy, that means that we can produce very excited species following the photoionization, like in synchrotron or low energy collision experiments. And we also have the short pulse duration that give us access to picosecond, femtosecond, or attosecond timescale. And because of these two things, we expect that the dynamics will be driven by electron correlation or non-adiabatic couplings. In fact, there are not so many experiments trying to investigate these short timescale dynamics induced by the XUV pulse. And there are only few experimental results on relatively small systems showing that the multi-electronic effect and non-adiabatic couplings following XUV excitation can be investigated in real time. And our goal is to push these kind of experiments to larger molecular species. And we have seen in the previous talk some example of dynamics induced on few femtosecond timescale. So we perform our experiments using high harmonic generation to synthesize short XUV pulse. So we focus a femtosecond laser on a gas target, and we can filter the harmonics that are produced. And we recombine the XUV pulse with an infrared pulse, and we focus both pulses in our spectrometer, and we control the delay on the femtosecond or attosecond timescale. So this is our attosecond beamline in Lyon that we have developed as a collaboration with a group of Eric Constant. And we also have a long-standing and very fruitful collaboration with a group of Mark Wracking at Max Born Institute. And I will show some experiments that we have performed here, and also a collaboration with a group of Giuseppe Sansone. So let me start with XUV-induced dynamics on femtosecond timescale. So that's an experiment that we have performed at the Max Born Institute, and we have studied a few pH molecules of various sizes using the combination of a pump that is an XUV 25 femtosecond pulse with a spectrum centered around 20 eV. And it is followed in time by a short infrared pulse, 30 femtosecond, and at weak laser intensity. So what happens when we shine the XUV pulse and when it interacts on the pH molecule with the pH molecules, we always obtain this kind of fragmentation pattern that we record with the time-of-flight mass spectrometer. So we always have ionization signal, so ionization of the molecule and double ionization of the molecule, and H loss, C2H2 loss. Then when we include the infrared pulse, we can measure this kind of map, that is the signal that we measure with the two pulses minus the signal that we obtain with XUV only. So here is a mass distribution, here is a delay between the two pulses. And when the signal is positive, it means that the infrared pulse has increased the number of ions. And when it's negative, it means that the infrared pulse has depleted the channel. And we focused our interest on this specific ion, so that is, in that case, the doubly charged anthracene molecule. And you can see here that there is a fast variation of the doubly charged cation of the anthracene, and it is followed by the depletion of the singly charged anthracene. We can extract a time constant from this measurement, and it gives something like 30 femtosecond. So, in fact, we observe this effect for different pH molecules, and you can see here that the time constant smoothly increases with the size of the pH. We have also investigated the effect of the laser parameters. So by changing the generation gas, we can change the XUV spectrum. And when we change the XUV spectrum by increasing a number of photons at high photoenergy, so increasing the spectrum like this, we don't see any variation of the decay of the time constant that we measure for each pH. And when we change the laser intensity, the probe intensity, we also don't see any variation. So that means two things. First of all, the dynamics that is created is induced by the lowest harmonics of the spectrum, and the infrared only acts as a probe. So it does not affect the dynamics. So it is really a dynamics induced by the XUV. So the interpretation of this experiment is given on this picture. Actually there are two steps. The first step is photoionization. And we see that since the work of Lorenz Sederbohm, we know that electron correlation and multi-electronic effects are very important for this kind of molecules at this photon energy. So what the XUV pulse does, it ionizes the molecule and it creates excited cationic states. And these excited cationic states, they can be ionized by the infrared pulse, leading to the decations that we measure in our experiment. Of course, these excited states, they cannot remain excited, they will decay, and they will decay through non-adiabatic couplings. So they will decay to lower energy states up to the point where the infrared pulse cannot ionize anymore. And that's what we measure in the experiment. So this interpretation is supported by calculations that we have performed on naphthalene as a collaboration with Alexander Kulev from Heidelberg. And this is the result of a multi-electronic calculation. So here it's the ADC spectrum from naphthalene. So these are the cationic states that are produced for naphthalene when it is ionized by the XUV photon at 30 eV. And in this spectrum, the high of the peak corresponds to the monoelectronic character of the cationic state. So that means that if the peak is high, the cationic state is essentially monoelectronic. And you can see that for increasing binding energy and above 10 eV, the number of states that corresponds to so small peaks, so corresponding to cationic states that have strong multi-electronic effects, are increasingly important, and above 15 eV, they actually dominate the spectrum. So we have investigated the states in the region just below the double ionization threshold in a few eV range. So these are the states that can be further ionized by the infrared pulse. And we have built this non-adiabatic model. So we build the potential energy surfaces along the normal vibrational modes of the molecule. And this is one example, again, for naphthalene and for a CH bending mode. And the relaxation will occur when the states are crossing, so through conical intersections. So of course, we have to do that for all the vibrational modes of the molecule, and the relaxation timescale will be given by all the crossings of the states in these multi-dimensional energy surfaces. So the relaxation timescale will be determined by the topology of the conical intersections. So this is a result of the MCTDH propagation, and what is striking here is that most of the states, they decay within 30 or few 10 femtosecond timescale, like in the experiment. And we also see very short, even shorter timescale dynamics and some oscillation due to conical wave packet oscillation around the conical intersections. So basically what we have seen an ultra-fast relaxation that we observe for all the pH molecules on a few 10 femtosecond timescale, and it is determined by the way all these potential energy surfaces they cross. And this is in the region where you cannot neglect electron correlation. So in fact, we were wondering whether this kind of experiment and short timescale experiments with short XUV pulses could be interesting for astrochemistry. And we developed these ideas with Alexander Tillens, with a world-known expert of the question of the complex molecules in space. So we know that there are spectroscopies that have been able to identify a large number of very small molecules in space. But the question remains how complicated these molecules can be. And this is a very important question because, of course, complex molecules, they will lead to appearance of biomolecules in space and appearance of life in the universe. And directly related to this question is the famous unsolved problem of the diffuse interstellar bands. So the diffused interstellar bands are absorption bands measured by telescopes. And the intensity and the width of these bands, they suggest that they are produced by large molecular species that are excited and that have a lifetime that is below few picosecond timescale. So typically on the order of few femtosecond timescale. So discussing with Alexander, we realized that in our experiment, we use XUV pulses to produce directly cationic states and to measure the lifetime in real time. And we also observe, and we end up with few 10 femtosecond timescale. We see that the timescale increases with the size of the molecule, and we also see that this is a timescale for the highest excited state. So if you compare to what is relevant to the astrochemistry question, you find out that these molecules, and especially the bigger ones, they might be responsible for the dips. And the pH molecules, it has been a question under debate for already many years, whether or not they could be good candidates or carriers of the diffuse interstellar bands. And this kind of experiments bring some new information on that. But to address the question in a more general way, is it interesting to use short XUV pulses to perform femtoastrochemistry experiments? So experiments on short time scale that are relevant to what we observe in space. And actually, it is very interesting because what Alexander told us is that we have a way to monitor a lot of processes on radicular species, but also processes that are induced by the XUV and that are also very important in astrochemistry models. So we have an ongoing collaboration with Alexander Tillens and also Christine Joblin from Toulouse. And we perform experiments in Lyon and also some experiments in the group of Marc in Berlin. So going back to fundamental ultra-fast molecular physics, I would like to show you another example where nuclear motion has an influence on the dynamics. And this is an experiment that we have performed in Milano in the group of Giuseppe Sansone. So this is a very similar experiment. We use an XUV pulse to ionize a neutral molecule, a neutral caffeine molecule. And then the molecule is followed the XUV pulse is followed by the infrared pulse. And what we observe in this experiment, we observe that during few 10 femtosecond timescale, exactly 40 femtosecond timescale, we can dissociate the molecule very easily, and we can dissociate all parts of the molecule. And after a few 10 femtosecond timescale, we only can produce this part, this fragment, so the left part of the molecule. And the interpretation is that is given here, or at least we have some preliminary calculation. And initially, the XUV photoionization produces a hole that is in blue here. And the hole is fully delocalized on the molecule, so we can fragment everywhere. And then after a few 10 femtoseconds, you see the hole is getting localized on one side of the molecule. So this was a few examples of XUV-induced dynamics on femtosecond timescale in these complex molecules. And now I would like to show you work in progress on XUV-induced dynamics on sub-picosecond timescale. And the first example that I would like to show you is related to rabbit-like measurement. So at XUV-IR attosecond photoelectron interferometry measurements. So we know in the attosecond community that we can perform this kind of photoelectron two-color interferometry experiment. And this gives access to phases of the photoelectron wave packet that is ionized. And it also gives access to variation of the photoemission time delay. So you can see that, for instance, in that paper. So we can have information on how much time it takes for the electron to reach the ionization continuum. And there have been a number of experiments performed on atomic targets, but also on surfaces, trying to explore this photoemission time delay. And we wanted to investigate this in a more complex molecule. So here it's naphthalene. And especially in this large sigma star resonance that is around 20 eV. So this resonance is around the energy that we have in our frequency comb. And we performed this experiment in Lyon by combining the attosecond pulse train with infrared pulse. And what we do, we measure photoelectron angular distribution by using a velocity map imaging spectrometer. And we measure the velocity distribution as a function of the delay between the pulses on the attosecond timescale. And that's the result of the measurement. So here is the photoelectron energy, the delay between the pulses. And you can see at some specific energies corresponding to the sidebands in an atomic-like experiment, you can see oscillations of the electron signal on the attosecond timescale. And even more interesting, you can see phase shift between the different energies. So we can also do it in a more careful way. So energy as a function of the phase. And where we have more two-color signal, here it's indicated in black. And you can see evolution of the phases here as a function of the photoelectron energy. So is there any variation of the attosecond delay? We don't know yet. We don't have the theory to answer the question yet. But we have investigated very similar things in the case of the plasmon resonance in C60. So there's a very well-known plasmon resonance in C60 around 20 eV. And we have shown that around this resonance, we can have variation of the photoelectron angular distribution. And this is due to a variation of the phase of the electron wave packet in the continuum, as usual. But thanks to calculations by Imadri Chakraborty, we have shown that this variation is indeed related to variation of the photoemission time delay. And this variation is in fact due to electron correlation effects. And we have also a general semi-classical model that has been developed by Thomas Barillot during his PhD in our group that also shows the same effect and that also matches very well the TD-LDA calculations. So now I would like to show you a last example. And this is about attosecond charge migration induced by correlation. So you can induce very short timescale dynamics in two ways. So you can superimpose, you can make a coherent superposition of cationic states. And then you can, if the energy between the states is large enough, you can have very fast dynamics. But you can also induce that due to electron correlation. And this is something that has been proposed by Lorenz Sederbaum a few years ago. And this is still something that the attosecond community would like to be able to measure. So what we have been doing as a collaboration with Heidelberg, we have been identifying a very specific case of Hall migration induced by the electron correlation in the case of benzene. And this specific attosecond dynamics, we call it attosecond charge breathing, because it looks like this. It's really just after removing one electron from the benzene, the positive charge kind of breathes around the carbon ring and the hydrogen atoms. So why does it exist? It's because it is known that for the benzene molecule, below 20 eV, there is a well-defined shake-up state that is completely isolated for other states with multi-electronic characters. And as I said, this shake-up state corresponds to the dynamics that is very specific, where the charge oscillates in and out of the carbon ring and in and out of the hydrogen atoms. And this motion, this charge dynamics, is in fact very rapid. It occurs in less than 1 femtosecond timescale. And you can see here the population of the orbitals that are involved in this whole oscillation. And we were wondering if we would have any chance to measure that in a real experiment. And to do that, to explore this possibility, we have made calculations, including nuclear motion, because nuclear motion is, of course, very important and can change the dynamics. And indeed, some vibrational mode completely destroys the dynamics. But if we include all the distortions with all the vibrational modes in the molecule, we end up with this result. So basically, the attosecond charge oscillations are still there. So they survive the nuclear motion. And even more important, we know that conical intersection effects only occur after 10 femtoseconds in this molecule. So that means that we have a lot of time to see this oscillation, and that might be observable in the experiment. There is another very interesting aspect in this attosecond breathing of the charge. It's the scaling effect. In fact, you can find a very similar breathing effect of the charge for different molecules that are similar to benzene. So for instance, the cornene here. And it just scales in a way that the dynamics is slightly longer, but it looks pretty much the same. And another last aspect that I would like to show you, it's when we plug a molecular group to the benzene molecule. So in that case, we end up with Francesca's molecule, phenylalanine. And we wanted to see what would be the effect of this group. And the effect is there. So you see that we still have the breathing of the attosecond breathing of the charge. So you see the fast oscillations. But of course, the group has an effect because it destroys, periodically destroys this oscillation. And well, this is expected. Okay, you change the molecule, you will have something slightly different. But what's interesting is that when you include the vibrational motion, well, we know from what I've shown before, we know that it does not affect the whole dynamic in the benzene, but it does on this part of the molecule. And it does influence the role of the effect of the molecular group to the benzene. But it does it in a way that it actually brings the whole breathing back. So when we include the nuclear motion, we actually don't have any effect on the benzene, but it destroys all the contribution, all the influence of this charge, of this molecular group. So we think that it's very interesting because it means that this kind of correlation-driven Hall dynamics in aromatic species seems to be present in every kind of molecules like this. It's robust. It's not influenced or weakly influenced by the vibrational modes. it's faster enough than conical intersection cannot play a role. So that's the right candidate to observe these kind of things. So finally, I would like to thank the people in my group in Lyon, and especially Victor Després, Alexandre Marcignac, and Thomas Barrio, who have done a lot of these experiments, and our co-workers on the pH benzene project, people in Bordeaux, on the C60 project, and on the caffeine project. And thank you for listening.